that I've had a number of collaborators that have joined me in this work, most notably those from the Norwegian University of Science and Technology, NTNU, as well as members from Argonne National Lab. And I would like to point out, of course, the financial and facility support from those that you see down here. And lastly, I always love this photograph because it's from our new campus, which shows a state-of-the-art library, which is everything except what you would expect from a library. So let me go ahead and talk a little bit about our motivation. First of all, most gases that are commercially relevant are not pure. They contain diluents, and those diluents are usually byproducts of chemical reactions. So if you start looking at the water-gas shift reaction, for example, which is primarily notable because it produces 96% of the global volume of hydrogen, it comes with carbon dioxide, which has to be removed. Likewise, CO2 can be removed from methane, and so that's called methane sweetening. So these types of separation activities are quite important, and they are responsible for giving us the types of gases we need in a satisfactorily pure component. And so if you look at the research that has gone on in this area for many, many years now, initially there was this keen interest in hydrogen purification. And that's actually not a trivial separation considering the sizes of the molecules. The same type of separation is directly applicable to liquids as well. So if we start thinking about water purification, that's also a molecular separation. But let's concentrate right now just on CO2. So of course we know that CO2 is the major player when it comes to global climate change. So we do need to be able to remove CO2 from effluent gases. And that's not the only reason why we want to be able to extract CO2. The other one is for air purification. And while we don't need to worry about that on a daily basis, we certainly do need to think about it when it comes to extraterrestrial travel, or even for first responders who are reliant on oxygen packs that only contain so much oxygen. Even more recently, there's a growing need for CO2 extraction in the tubing of ventilators for those in need in hospitals. So there are a lot of really good motivating factors to remove CO2 from mixed gases. There are three strategies by which this can be done. The first is to remove CO2 based on its size, and we call that size sieving. The other is we can rely more on chemical affinity, and that's a solubility-based separation practice. And the last one is based on chemical reaction. Well, I'm going to be talking primarily about the first two only, but I would like to leave with the point that what is developed for CO2 can usually be more broadly applied to other diluents, and those can include acid gases as well as basic gases. So, a very quick look at molecular transport. There are two important metrics that we have to think about. The first is the permeability, which is a measure of throughput. The second is selectivity, which is a measure of separation quality. And typically, the mechanism that is obeyed by a penetrant molecule is what's called the solution-diffusion model. And in this case, what we have is a three-step process. In the limit of Fickian diffusion, we have first absorption onto the surface of an organic membrane, then we have diffusion through it, and then we have desorption. And the only types of membranes that I'm going to be referring to today are those that are considered dense. That is, they are non-porous, okay? And one last thing that I should point out is that In this limit of a solution diffusion mechanism, the permeability can be described as the product of the diffusivity times the solubility, in which case the selectivity can be broken down into both a diffusion selectivity, which is what you see here, and a solubility selectivity, which is seen here. Okay, so that's important because when we talk about size selectivity, that is equated with diffusion. And so you can usually say that you have small molecules diffusing faster than larger ones through a dense polymer matrix. Whereas if you have a reverse-selective membrane, it's based on solubility. And in this case, large molecules actually can permeate faster than smaller ones. Now, as you might have thought, these two categories depend on free volume, with diffusion selectivity found primarily in glassy, that is high glass transition temperature polymers, whereas those that are solubility selective are usually rubbery polymers that have a low TG. Now, there are ways in which you can start playing around with free volume or chemical affinity. One could add in either a plasticizing agent or an anti-plasticizing agent to change the TG, or introduce cross-linking, or introduce nanoscale objects that can change the way chains pack together. But the one that I'm going to focus on today deals with physically tunable nanostructures that occur inherently in polymer systems. And so the first example that I'm going to touch on deals with Nafion. Nafion is a very well-studied polyelectrolyte that is used primarily in fuel cell technology. And what we're going to do is take Nafion, which is inherently nanostructured. It contains nanoscale channels that are hydrophilic that allow for permeation of water. And into this, we're going to introduce an ionic liquid. So the principle behind what I'm going to be talking about is shown here. First, we start off with the Nafion. And the sulfonic acid groups here that you see form clusters. And these sulfonic acid groups are inherently hydrophilic. We're going to add in an ionic liquid that will tend to bind with the sulfonic acid groups and thereby increase the size of these channels. And then we're going to add in water, which will swell the system even further. So here is a transmission electron microtomograph that shows the three-dimensional structure of Nafion, and you can see the nanoscale channels through which water transports. This is a random copolymer, so there is no order to these channels. And this is the ionic liquid that was selected based on its miscibility within Nafion. So if we start looking at the effect of the ionic liquid, you can see that for CO2 as well as other gases, as soon as you start adding in the ionic liquid, the permeability increases significantly by close to 2 orders of magnitude. That's not too surprising since ionic liquids in general tend to be CO2 philic. If we now introduce another aspect here, namely humidity. Humidity is our source of water for the system. Once again, you can see that as we increase the amount of ionic liquid, the effect of humidity becomes more and more pronounced. And ultimately, we can get up to very high permeabilities on the order of about 400 bar. And that the bar is a unit that's commonly used to describe permeability. So this is a relatively high value since most of the best CO2 removal membranes have a permeability of about 100 bar as a point of reference. And from small angle X-ray scattering, you can certainly see how the microstructure or the nanostructure, of the Nafion is changing as we introduce the ionic liquid. So we have a material here that can be easily tuned in terms of its CO2 transport properties, either by adding in the ionic liquid or by adding in the ionic liquid followed by introduction of humidity. Now let's see if this idea can be transposed into another nanostructured polymer system. And for that, we're going to look at a block ionomer. This is the chemical structure of the block ionomer. It contains hydrophobic end groups on both sides and a partially sulfonated middle block. And this particular design is important because those hydrophobic end blocks hold the material together very nicely, even in the presence of a polar liquid. So this material is amphiphilic, and it is also solvent tunable. So as you can see from the TEM images shown to the right here, depending on which solvent we use, whether it's tetrahydrofuran or cyclohexane, you can see that the morphology of the material changes considerably. And the first two images in both of these series are really just to demonstrate that different staining agents for TEM can stain different moieties. And this is the one that is really important because this stains the sulfonic acid groups. So now you can see where the ionic microdomains are, and you can see the pathways for diffusion as CO2 comes into the system. So here are two examples of the same material with the same morphologies I just showed, the small angle X-ray scattering patterns for each, and you can see that the THF cast is far better ordered. The lamellar morphology is actually the preferred equilibrium morphology of the system, but even the cylindrical ones that you see up here have a continuous ionic matrix. If we look at the permeability of ammonia through these membranes, you can see that ammonia being a base gas very much likes the polyanions within the block ionomer. And so you can see that the permeability of ammonia is very high. It's higher in general in the case of the system that exhibits a continuous ionic matrix here, whether it be cylindrical or these channels that are lamellar. But the important aspect is that once these are humidified, they actually work a whole lot better. And this permeability over here relative to the permeability of nitrogen down here gives us a selectivity that approaches about 2000. So it's a very, very highly selective system. Well, that's for ammonia. And this is important because one might want to purify something like biogas. Then we have CO2. And so before we can talk about CO2, let's talk briefly about water, because it's important to realize that water is going to play an important role in CO2 permeation. And compared to Nafion, the solubility of water is much higher as a function of relative humidity, and its diffusivity, while it starts off a little bit lower, actually becomes close to an order of magnitude higher at higher relative humidities. What does this translate into? Well, it translates into relatively high CO2 permeabilities. And it's important to recognize here that there are two different experiments. There are single gas measurements shown as the open circles, and the X's are mixed gas measurements, which take into account plasticization that may occur due to CO2. And there's absolutely no difference between them, so we can assume that CO2 really does not plasticize this material. The Nafions has a slightly higher permeability, but when we start looking at the selectivity, we'll notice that the selectivity continues to go up, whereas for Nafion, it tends to level out. So there is similarity, but there's also difference. If we take the same materials now and we expose them to water, liquid water, well, this morphology that you see here has been examined by electron tomography. And these are now snapshots of a three-dimensional reconstruction. And it's meant to show you that some of these micelles that you see over here, and these are contrast reversed, just to better show them. Some of them are quite liberally dispersed. They are not connected, while others are connected. And in larger populations, some of these micelles actually form clusters that are connected. When we put this in water, the entire morphology reconstructs or forms into one that is more continuous. And that's important for water transport and CO2 transport. In fact, if we look at this carefully, for different solvents that are used in production, we find that before submersion in water, that the permeation for all those that exhibit relatively ill-defined dispersed morphologies give about the same permeability, whereas THF is better. And in terms of the selectivity, it turns out that all of these dispersed morphologies are actually better than THF cast because we wind up having continuous pathways. But once we change the morphology, now all of these tend to give extremely high permeabilities, and the selectivities remain relatively the same. If we put this on what's called a Robeson plot, which shows us the balance between selectivity and permeability, there's a naturally occurring upper bound, and that is produced by looking at thousands and thousands of different types of materials. And what we find is that some of these actually start to exceed that upper bound. So now we're going to look at the last example. In the last example, I call gate opening here, because what we're going to do is we're going to look at putting together two different types of species in the same nanostructured membrane, but they're going to have opposing attributes. One is going to be size selective, and we're choosing nanofibrillated cellulose for that. The other, which is solubility selective, we're going to use humidified ionic liquid again. And so the idea is that without the ionic liquid, the nanofibrillated cellulose basically acts as a barrier to everything. Nothing gets through. If we put in a little bit of ionic liquid and a little bit of water vapor, then we can open up these channels a little bit as well and allow the CO2 to pass through. If we put in too much of either, that's when everything goes through. So let's see if that hypothesis works, where we go from a gas barrier to size exclusion, ultimately to no effect on transport, but we do have mechanical reinforcement. So here are some STEM images that were obtained from the nanocellulose, and you can see that from the elemental maps, the nitrogen that's associated with the ionic liquid up here winds up staying onto the fiber, which is good because that shows a chemical complexation. If we look at water, we see that as we start to add in water to the system at higher ionic liquid levels, it increases significantly. But the diffusivity does something strange, and that is that when we have either pure cellulose or just a little bit of ionic liquid, then there's this very strong dependence on diffusivity with water. But once we get up to 35%, the water seems to have a continuous pathway. So it looks like there's a transition that occurs here. And in fact, if you look at permeability versus relative humidity for single gas measurements, you see a maximum at 60% humidity when we have 35% ionic liquid. This is also reflected if we start looking at single gas measurements using nitrogen, methane, and helium. We do tend to see this significant increase in selectivity when we have 35%. If we do mixed gas tests, we see the same thing. And so what we've come to realize is that our model is actually quite accurate, where we have barrier, we have gate opening, and we have mechanical reinforcement. And if we put this onto a Robeson plot, you'll see that we actually get well above the upper bound for many of these materials, which gives us a new way to start structuring these membranes for CO2 removal. So with that, I'll leave you with my concluding remarks to point out that we can purify valuable resources, we can protect our environment, we can deal with acid and basic gases, We can use nanostructured polymers to introduce hydrophilic nanochannels for CO2 transport. We can use ionic liquids and humidity in concert. And lastly, we can even introduce nanofibrillar materials to yield size-selective or size-sieving selective membranes.